Well, thank you, first of all, for having me, for introducing me and the kind words that you gave to me right there. And thank you for having me here today back in Texas. It's been quite a while. I think the last time I was in Texas was for the 2019 Acadia Conference in Austin. The last time I was in Dallas was 20 years ago. So I was in the same position as you all, as an architecture student visiting from San Antonio. So today, I'm going to focus my work. I'm not going to be talking about robotics or anything. I'm talking about something different for the first time in a while, and that's the projects that I've built over the past, I don't know, a while that deal with lightweight structures. And for the most part, these are going to sort of talk about carbon fiber, but I'll also touch on a few other projects as well. One thing you'll probably notice is I don't take my work as serious as maybe I should. I think everyone should have fun with their work, even if the project doesn't turn out the way that you expected it to. Anyway, I'll get started by giving just a brief background on where I've been, because I think it's really important, again, as a student to understand that the trajectory that you think might not be as simple as you think it is. So over the past 15 years, after graduating from grad school at MIT, I've had the pleasure of working all over the world and presenting my research and talking all over the world. I've worked in Japan and China. I've presented and lectured on almost to all continents now. So it's fun to get to go around and meet people all over the place. I focus both in research, but I have also spent a lot of time in practice as well. And so prior to coming back into teaching full time, I did work in San Antonio, in Tokyo, and with a lot of projects in China. Some of the things that are really sort of important to me from the beginning, where you all are right now, are crafting and collaborating. And so I think one sort of important thing for everyone to keep in mind in architecture is it's not really about one person, right? There's never one person making a building. You're always working with a team of people. And I think it's really important to understand that. And they could be people in architecture, or they could be a sculptor, or they could be a ceramicist, or they could be whoever, right? And so all of my sort of build works kind of started here. This was a lightweight structure that I had designed in my final undergraduate studio at the University of Texas at San Antonio. It's still standing somehow. That was 2005. This picture was taken in 2018. They actually installed everything backwards, but it still works somehow. So it's good when people can reinstall things and not know how it works, and it still sort of turns out okay. But in those early sort of projects, one of the things that I really got interested in was new tools. And so this is again back in 2004, 2005. And at this time we were using, we basically got access to a giant fabric making shop. And this is a 60-foot long CNC mill for CNC cutting fabric. And so we designed and we built a series of these structures. During our studio, we learned how to sew. That was one of the first things I learned how to do, is I bought a sewing machine and just started going. Then from there, we scaled up. This is an RF welder, apparently very dangerous, but they still let us use it. This was for welding fabric together. And basically from this, I've continued to make. And some of it is very sort of choreographed. I make digital models, computational models, and know how everything goes. And sometimes I'm just I'm going to do something. And there are no drawings, and it freaks out a bunch of people at my school because they're like, you didn't make drawings for that? Everyone needs to make drawings. And no, you don't always need to make drawings. So at Ball State, I kept going when I was teaching there. I always work with my students when we're doing build projects. I work with all different types of people. So this is Tim. He's a sculptor, so we do a lot of hand making. I work with people who have skills I don't have. I don't like working with welding because I would probably kill myself, so Tim helps me on a lot of my projects. I work with new tools. This was a project that we had done with Photogram when they were prototyping their steampunk pavilion. Tim Rusterholtz, the sculptor, and I, and then Chris McAdams, who works with VR, we worked with them to develop a system for them to build their project. So we work with different tools, but I also work with different materials. And so this is for a project I'll talk about later also. These were kites that had phase change material embedded in them, where we were looking at how to sort of, can you make clouds through kites? And I'll explain this later. But so again, lightweight materials and different types of things we don't typically think about in architecture. And that goes to like robotics. And so I like working with hands, but I like working with tools, whatever they may be. And so if you come to Temple, you'll probably see me building something in some random place. And so that's me taking over the sculpture gallery. They were not happy about that for a long time. And sometimes I'm just like in the hallway making stuff randomly. Usually they're not happy about that either, but it's fun. So in research and making, there's a few sort of things that are really important to me. And the first of all is collaboration. I'll talk about this more later, but I like to work with everyone. It usually winds up being problematic because then I have too many projects and not enough time. Computing, I think, is really important. Working with the newest sort of tools that we have, but also referencing the old, right? So it can't just be one or the other, it has to be both. Making, of course, all of the projects that I'll talk about today were made. Material, I think, is also important because from modernism, we've been sort of told that we have a palette of materials, right? You go to Home Depot, you get plywood. You have flat things that are perfect, but not everything in the world is perfect. So why do we work with these perfect materials all the time? And then machines. Those can be autonomous machines, or they can be machines that we control. They all sort of goes, whatever I need, I try to use in my work. And so this is just sort of, I'm not going to talk about all these projects today, but this is just some of the projects that I've mostly completed over the past 10 years, with the exception of the top 3. The other one is from graduate school, so I kept building stuff at MIT. So we have flying stuff, we have floating stuff, we have stuff on the earth. I feel like I'm missing something else. Nothing's caught on fire yet. So, but we have trying to push the boundaries in terms of how things are made. So today, basically the projects I'm going to talk about are what I'm calling lighter than air. They're not really lighter than air, but they're lightweight structures. And that was sort of, for me, I was sort of inspired by like Norman Foster came and lectured when I was at MIT, and he was talking about Buckminster Fuller, like talking to him one time, like, hey, Norman, like, how much does your building weigh? And he was like, I have no idea how much my building weighs. And so then he tried to figure out how much his building weighed, and seemed to be very shocked when he realized like how much material actually goes into it. And that's something that we don't typically think about when we're designing, right? Like how much material is going into the things that we make. And it makes a huge difference, right? Like if your building weighs like 1 million pounds because you used concrete, like it has a big impact on the earth, right? All of those materials come from somewhere. It's just like a 9,000 pound car, right? Like why does your car need to weigh 9,000 pounds when you weigh like 200 pounds? Like it doesn't make sense. And so we should think about that in our buildings as well. And so, again, these projects will have a different level of seriousness. This is not a very serious project. So I thought I would start with that. This project it's made from carbon fiber. It's roughly around 25 pounds. It's flat pack. So every project I try to do it in a different way. And so this one, we had a really big kiln. We were working at Autodesk in Boston. And so we're like, okay, let's see how big we can sort of go with that. And I was using carbon fiber cables that I was hand making, and then 3D printed connectors. I was working with my friend Simon Kim, who's an architect, and then my friend Tim Rusterholz, who's a sculptor, and we all have weird ways of working together. So like I mentioned before, projects don't always go the way you thought they would. And so Simon and I at the beginning were very interested in sort of moire and like the form of this thing and what it would look like, but we very quickly realized that like the material doesn't want to do what we want it to do. So it sort of evolved into another project, and that evolved into another project. So this was the first sort of small scale prototype where we began looking at basically like layering of shadows and cables. And so the one sort of interesting thing about carbon fiber, if you don't know how it works, is it's basically, when you get it, it's like the fabric in your shirt. It's like thousands and thousands of microscopic pieces of carbon that are bundled together. And so you can do anything with it. But if you imagine trying to make a building out of a shirt, it doesn't really work very well, right? But the cool thing about this is that what we're using, you solidify it in a kiln. So everything I make, we put it in a kiln, and it goes from like a fabric into solid. And it's done through like resin that's impregnated in it. And so we did this sort of little iteration. It was like, oh, this is kind of cool, but it's really sort of wiggly and not really doing other things. And so the scale of it was roughly me on my knee like that. But this was the sort of effect that we were trying to get with that. And so the question was, now that I built this thing and Simon and we brought Tim in, it's like, okay, well, what does this thing really want to be now? Because it could be this, but it could be something else. And so it became some sort of like other weird project. Tim was like, yeah, what if it's sitting on some weird distorted sculptures of like Greek gods that were distorted? And it's like, yeah, why not? So sometimes you just do things that are weird. And then the other part of this, which was with me and Simon, was like, how can we make these things become more sort of rigid in what we were doing? And so we went to Autodesk. This is the build space. And we basically developed a flat pack system for fabricating all of these modules. And so Dinner for Six basically comprised of like 4 unique modules, each which are roughly like human scale. You can go into each module. And those are all built from either flat or doubly curved panels like this. And so basically the only design work for the panels, besides having the outline that we did, was figure out how we wanted the winding. And so this is just an example of a winding pattern. Why this project is sort of important for me was this. And this image might not make any sense to anybody, but basically what this is we took carbon fiber, which is usually just wound, and we made it into cables. And it's a very time-consuming process because first you have to like string all the carbon fiber, and then you have to like wrap it by hand. And so one thing that I've realized is that you can use robots for some things, but you can't use them for everything. Some things need to be done by hand. So this is just a detail of the piece. Like one module, and then looking at the sort of the whole thing within the Autodesk space. And so this is basically the scale of that piece. We set it up here, and then we went back to Tim, and we were like, okay, Tim, like let's look at those weird characters now. I just have to show them just for the heck of it also. And so Tim is an amazing digital sculptor, but he also is a hand sculptor. And so he has the digital skills that most sculptors don't have, but he's still able to like produce things by hand. And so these are all CNC milled on a really big 4-axis mill. And so basically you put a plug in and it rotates, and then it milled the heads out of that. And so these are like sort of famous busts, but that one's almost invisible on the screen. But they're all distorted in a weird way. This is the Zuckerberg. It just kind of looks like a squished Mark Zuckerberg. So we kind of named these things also, which makes it more fun. So we made all of these things, and then we just kind of like, oh, let's put the two things together. And so you get the carbon fiber thing sitting on some weird heads, but why not, right? It's a fun project, whatever. So everyone should have fun with what you're doing, right? So a project that's a little bit more serious, not quite, I don't know. I don't know how to judge seriousness anymore. But Roly Poly was a project that was actually before Dinner for Six, but this was with Simon Kim again and Tim Rusterholz, the sculptor again. And so this one is about 15 pounds of carbon fiber. It was a thinner 12,000 strand carbon fiber. The other one was 24,000 strand. And it's basically a monocoque structure. So it's just one sort of unit. And the goal for this sort of unit is that somebody could occupy this in any direction. So you could sort of get in it, and you can just sort of like roll around in it if you wanted to. Why? I don't know. Because it was fun, I guess. And so this is sort of what it wound up. This is the end result of the carbon fiber piece. There was also an interactive element, but I'm not going to talk about that today. But again, the first thing that goes for me, like we come up with the form, and then it's like, okay, well, how do we build this thing now? And so It's partially handmade and partially laser cut. And so we laser cut all of these like gripper teeth. We built our own tools. So in order to make the frame, we had to make custom curvature because one of the things that, if you're working with fibers or fabrics, the thing that you want to have is like double curves. You don't want to have straight lines. If you have double curves, you get strength. And so every single piece of this thing was uniquely double curved. And so Tim and I just sort of fabbed up this custom rod bender. And then there was lots of sparks and welding, and we basically created this frame that then all of those gripper teeth would go on. And so Tim welding again. And then figuring out the details, like there's no sort of playbook for any of the details that we do. We just sort of make them. So just some Home Depot stuff in there. We have some like bar clamps, and then I guess another bar clamp. We've got some leftover steel rod in there from the cutoffs of the scraps from the other piece. And then the laser cut piece, the laser cut gripper. From there, we basically began thinking about winding patterns. And so for this project, one thing besides the just occupying it in any direction, one other thing that was really important was sort of a variation in porosity. And so one thing with buildings is that you either have like transparent or you have solid, right? You have glass back there, you have solid wall here, maybe you have slats, but you don't really have gradients. And so we began looking at how to create gradients in our work. And that took the form of like some digital modeling, but then also a lot of hand winding tests with string. This string gets reused in another project, so that's the other thing. Very low budget on all of these things. And after sort of the tests, we basically wind it. This is the kiln that it was fired in. It's roughly 6.5 feet cube. This is not finished, it's just storage. It was in the ceramics department. They didn't want me taking up all their space, so we had to store it in the kiln when we weren't building it. This is the final piece that has been completely wound. And like another sort of thing that was really interesting about carbon fiber that we learned about with this project was that the appearance before firing and after firing are completely different. And so for this project, or right now, before firing, it's very sort of dull. But after you fire it, it becomes very sort of like glossy, which was really sort of interesting when you're sort of like in it or around it. Another thing you can see here that I talked about the double curvature, you'll notice that there's lots of overlap. And so another thing that when you're working with materials like this is that you have to like overlap them. And so you need a curvature and you need overlap in order to make it strong. And then after it's fired, you basically wind up with the final product. And then occupied in any direction. My son tried to occupy this. He was terrified. So do not try to put a 3-year-old in your project. So only pictures of him looking very sad. I will not show those today. So for him. So as you can see here, I'll just flip through sort of different orientations of this. But basically, it's stable in any direction. This still exists. It's under the staircase in our building. I just refuse to throw it away, and nobody's brave enough to throw it away. So, but anyway, so this was a fun project. But I think the part when I look at this, again, the thing that was most important for me, besides learning about the material more, was sort of the porosity in here. Things that we can't get from traditional architecture materials, right? Like, how can we use the tool, like new tools or new materials, to create things that we don't typically have? And so for me, this was sort of like an eye-opening image, just looking at like the density on the right and then the porosity on the left. And it's all determined by the person who's making it, right? So it could be whatever you want it to be. This is the only This is the only non-carbon fiber project I'll show today. This was the Underwood Pavilion. It was a summer design build studio at Ball State University when I was teaching there. So it was a 5-week design charrette. The design really came together in week 3.5. And then we basically figured out how to make it work in the next week, and then we built it in the next 5 days. This project is the most heavy project also. It's about 100 pounds. It's made of aluminum tubes, steel cables, turnbuckles, and earth anchors. And so this is sort of the final piece, and it's one of the faculty members, he had his own little lake in his house, so we put it there. It lived there for like 2 or 3 years. But for this project, we were really, everyone was really sort of interested in the tensegrity. Here's like Bucky Fuller with a tensegrity model. The one problem with tensegrity models though is they're very much they're very difficult to calculate computationally. And so most of the stuff happens by hand. And so our goal for this project was to find a computational means of building the structure and then basically building it. So we started with the site and what we wanted to see in the site, like all of you probably do. And then we began coming up with a method for computationally defining this through Grasshopper and like a physics engine. I'm blanking on it. Well, Kangaroo, and then there was a lot of things in here. This was like 8 years ago now, so my mind is sort of blanking. But we started by creating a module and looking how the module changes in tensegrity. Then we began looking at individual components of that module, so cables, struts, fabric, and we basically calculated all of those. And we looked at how all of the things basically go together, and so like the patterning of fabric, and so a lot of, with lightweight structures, a lot of the stuff that you're doing is like patterning, whether it's carbon fiber, figuring out the pattern of how you wind, or in a big fabric, like in the project I did at UTSA, like actually cutting the patterns, or in this with the stretchy Lycra, understanding how the material stretches around the frame. And so in 2 days, we fabricated all of the pieces in the wood shop. They did not appreciate that because we were cutting aluminum in the wood shop, but it got done. So, and then we basically, along the way, we mocked up all of these things. And so this is a mock-up of one module with no fabric, and then the other module and how they sort of go together. Looking at how a module sort of gets bigger. So we start at the module, and then you begin looking at rows. And what happens when you put tensegrity rows together? And when you begin aggregating these things, they begin to turn. And so you need to understand how they turn. It also becomes really difficult to build these things because every module adds tension into the system that just becomes more and more painful as you go along. So by the end, it was not fun. And so you could see here some of the students, and I'm always there taking pain with the students, building this with them. And so we were there testing, laying out all the modules, and so this is all the modules. And then from the individual sort of strands, we began looking and simulating how the entire surface begins to come together, because a module works different from a line, and a line works different from a surface. And so we had to figure out how to calculate all of those. And the sort of the forces that go into all of this, and then beginning to think about apertures. And so we didn't want this to be just like a really dense structure. We began taking pieces out of it, so that way you get like little skylights in there once you're in the piece. That's Andrew and Nora building this thing from the inside. The little orange rope that's going around, it's so that we know where we are, because it's impossible to tell where things are on this. And so you put one in, you tie the rope, and then you follow the rope, and then you like keep going and going and going. Oh, this is painful just remembering it. Sorry, like having traumatic memories. And then the last thing again is details, right? Like how do you connect all of these things together? And so we basically figured all of those out. And then in the end, it's Nora putting on the last piece there on the right. And it became sort of like it was a really interesting structure because of how light it felt. It felt like it was almost flying. When you look at it on the ground, it barely touched down. Like you literally had to anchor this thing or else it would just sort of blow away in the wind. And so the most difficult part was probably actually getting those earth anchors in at all of the points where it touches the ground. Otherwise, it would just sort of disappear. But again, the aesthetics of this, just like the carbon fiber, because we're working with these modules and we skin them in a particular way, from the inside, it's extremely porous, and so you get this really sort of nice view, but from the outside, it becomes very dense. And so, again, like controlling materials is something that I'm really interested in testing. Cloud magnet. This was with Rashida Ng. She's now at, she's the chair of Penn's undergraduate department, and Tonya was in engineering, biological engineering, something like that. So an interesting mix again. So this project weighs about 2 to 3 pounds. It was using 24,000 K carbon fiber. It's a phase change coated lightweight skin and phase change coated non-woven fabric skin. And these are just a very small number of the prototypes I mocked up for this project. So when I started at Temple, Rashida had received a grant for this project. And this project was tested in Monteverde, Costa Rica. And the problem that they're having there is that this is a cloud forest. And basically what's happening, the clouds are rising. And it's changing the environment of everything below the clouds. And so Rashida and Tonya had put a proposal together to create these cloud-making kites as an art installation, not to like solve the problem. Like, we're not going to solve the problem. But it was more like, can we fly these kites and potentially create something that changes, like that has like a stream of clouds or a puff of cloud? It didn't happen, but we got all the data from it, which was really good. So from this, I began working with Rashida, and we started with her initial sort of forms, and we began iterating with those. But the problem that we found was that carbon fiber doesn't want you to force it to do things. And so just like plywood doesn't want to be bent into a shape, like carbon fiber doesn't really want to be wrapped around stuff. Like, you can do it, but it makes making form, it makes it more difficult. And so the forms we were trying to get, like, they just didn't want to be that shape. And so this is just like, so looking at the detail of some of those ones where we forced it into this tunnel shape. And some of the winding details in there. This is ridiculously strong. I can stand on it and nothing will happen. But from this, the thing that I basically said we need to do is like, okay, we can't force the form. We need to let the form follow the forces within the kite. And so from that, we basically redesigned what the kite looks like. And the design of the kite was based on how carbon fiber winds together. And so these are the 3 kites that we tested. The bigger ones are 30 by 30 by 48, and then the smaller ones are 24 by 24 by 36. And so instead of starting with creating the form, I created a jig. So Tim helped me make the jig in sculpture again. And basically I started winding. And so we had certain constraints. We needed to get a lot of air at the beginning, at the front, and we needed to condense it into the smallest hole possible in the back. And I'll explain why in a minute. And so basically these are just some winding patterns that helped get the form. And from these winding patterns here, we began getting different types of forms like this. In the making process, another thing that I think is really important is, like, there's a lot of waste in architecture. So that string and roly-poly that I said was reused, it was reused in here as a means of creating a scaffold in which the carbon fiber was put on. And so one of the problems with winding carbon fiber is as you get tighter and tighter, the inner layers get looser and looser. And so in order to get rid of that problem, basically I wound like the green string first, and then the thing that gets loose is the string, and the carbon fiber stays tight. And so after you fire this in a kiln, you just remove the string and you use it again for the next project. And so this is sort of a detail of one of the kites with the string on before it was fired. The next sort of problem in here is, like, we need to get them to Costa Rica somehow. And shipping a giant box for 6 pounds of carbon fiber, it was like a ridiculous amount of money. And we're just like, we don't have that kind of money, so how do we make it cheap? And so how we did that is by varying the density in the carbon fiber. And so the big ends have less material, and so they were able to condense. And where we needed the strength down here where the most air pressure was going to be, that is dense. And so actually, these pieces all just sort of nested into each other. We crushed them into a very tiny container, and we shipped them to Costa Rica. And so this is in Costa Rica, the unboxing. And you can see that the end, basically, it comes down to a very tight point, and they basically nested into each other. And so as soon as they cut the zip ties on it, it basically unfolds into its larger shape. The next part of the project was the skin. And so for me, the carbon fiber is really important, but Rashida works with phase change materials. And so what is a phase change material? Well, it's a material that goes from one phase, like solid, to another phase, like liquid, when something is applied to it, like heat or pressure. And so the things that needed to be accomplished with these kites were a large volume of air needed to be pushed through to a tiny hole. And as that happened, it needed to get cold. And so basically what happens there, and sorry, there's just the frame itself, is the entire skin of this, another painstaking process, was covered in a phase change material that when the sun hit it, it got cold. And so the air that's pushed through is all of a sudden getting cooled by this. In order to keep it cooling, it had to spin. And so that was part of the other design part. It's like as it's flying, it sort of needed to spin. And so what we did is we basically took these to Costa Rica. Actually, Rashida did. I couldn't go at that time. We put a lot of sensors in them. And so with Tonia's help, we built a series of sensors that went in that checked humidity, they checked pressure, they checked temperature, and we monitored all of those things. And then a group of people, I don't know who they are, so I really don't know who they are. We built these in Philadelphia, and then they went there, and people did stuff. But anyway, they walked out into the cloud forest, and they very happily tried to make them fly. They did not fly. So it doesn't always work out the way you want them to. But the thing is that we were able to, over a period of 3 days, track the data. So look at how much air is going in, what is the temperature difference between the air inlet and the air outlet, and you can see that with the form and the sort of phase change material being embedded, they just basically put these up in there, so they weren't flying, but they were just like stationary. They were able to lower the temperature a little bit, and so there would obviously need to be a lot of other work that happens here in order to drop the temperature more, but we sort of, for a proof of concept, we were like, okay, well, this form works to generate the pressure we need. And the phase change material also basically lowers the temperature. The problem, though, is that there are like working temperatures that the phase change material wants to work with. And we can see that like when it's hotter at like 79 degrees, the temperature difference is it's really great, right? Like we drop the temperature 4 degrees, but once the temperature gets cooler, the number actually drops. And so one thing that we learned is we need to vary the different types of phase change material powder that goes into it so that it could work in cool or really hot. So I guess moving along, and I am moving fast. So I'll try to, slow it down a little bit. So moving from here, like I was working with my friend Masood, who's at Penn, and then just a weird image of testing something. Masood works with these things that are called spatial structures. And so everything I've been doing to this point was either a solid object or some sort of panel. And Masood was like, well, like, what if we could like make a three-dimensional like object that's actually really strong? And Masood basically developed this system called 3D graphic statics for determining structure. And we used his software that he developed to come up with forms for this. And so this is just like one sort of piece. We made a series of these pieces, and then we crushed them in Drexel's engineering lab. And so the question was like, carbon fiber is not meant to be used in compression. So like, could we do that? Like, is that really a thing that we could do? Like, why not try? And the other thing is that, well, if it can be used in compression, like, how much could it really hold? And so basically, we took these things in there, and we realized that, like, so this carbon fiber piece right here, it weighs like, I don't know, half a pound, maybe. It's probably less than half a pound. But if we look at how much it actually carried, it carried over 800 pounds in compression. So half a pound of material was able to sustain like 825 pounds of compression forces. And this is something that it does not want to do. It wants to be pulled, but because of how it was sort of assembled, it worked fine. And that sort of led me to my last project that I'll talk about today. I'm sorry, hopefully this wasn't like 15 minutes. I have no comprehension of time. And this was actually when Chuck emailed me about giving this talk, I was like, oh man, it's like I think I'm going to start up another project, but maybe I'm not going to start a project. Do I really want to do this again? And he was like, well, can you do a talk on lightweight structures? So like, okay, I guess I got to start this project. And so I was like, why not? Why not do it? And so I went with my friend Chad, who's an associate dean now, and I've been trying to get him out of his office for like 4 years. It's like, come on, Chad, you need to do some design work, right? And so I finally like pulled him out of his office, and we did this project together. And so this project takes what I've sort of learned from all of the others, plus the little crush test with Masood, to create something that I had never done before. And so this project, it's roughly 12 pounds of carbon fiber. The total structure with Chad's pieces are about 200 pounds. I used a wider carbon fiber, so each strand of carbon fiber in this had 50,000 strands. So you have to imagine this thing is like a 1/4 inch wide, but there's 50,000 strands of carbon fiber in that. And basically it's a spatial structure. So like with Masood's, the thing that I was working on with Masood, it's a 3-dimensional structure. So this is the final piece right here in our gallery at Temple. It was actually built for as an exhibition structure for Design Philadelphia 2022. So this was our school's project. Somehow I keep building our school's project. I don't know why that keeps happening, but it just keeps happening. But this was this year's project. So Chad and I, Chad did the 3D printed ceramics, and then I did the carbon fiber. I did the larger structure, but we collaborated together in terms of like how it looks and like what we wanted to do. And so, for instance, when I first put this together, Chad was like, oh, like, what if you put something through the holes in the center of it? And I was like, oh, that would be pretty cool. Like, why not do that? And so then I built something and just did it. And he was like, yeah, that works. So this was, so in disclaimers of drawings and things, this project was completely like off the cuff. There's nothing. I did a Rhino model of like a form, of just like the overall form, and I sent it to the people for the exhibition. And I was like, we're doing this. And they're like, okay. And it's like, just believe me, it'll work, right? And that was it, just a little Rhino model. I don't know if I have a picture of it in here or not. But I had a goal for what I wanted to achieve. And it was like, how can I build that form using a new type of structure that I had never done before? And so again, I'm always making stuff in weird places. And so this is our hallway by the entrance. And I was working basically there. This is the first module I built. This is this is the second module I built. So basically what I did is I had these 80-20 frames. This is the exact size of the smaller kiln that's easier to use. So it's the kiln is like 36 inches by 36 inches. And so there's 1 inch on every side for clearance in here. So I really wanted to maximize the module size. The reason for that is because the year before when I built it, there were like thousands and thousands of parts and like intricate Japanese joints, and it was just a disaster. It took like 12 hours to rebuild it 4 times, and I was just like, I'm not doing this again. We're gonna get this there in a minivan, dang it. And that's what we did. So there's like maybe 20 parts in this project, so another goal achieved. So these are just some more of the individual modules. You can see these are inside the kiln. And so these fire at actually a very low temperature, like 260 degrees Fahrenheit, so you couldn't even make a pizza with this. These kilns, it's really like they're meant to be fired at 2,000 degrees, so I can't even really turn on the kiln. I just turn on a pilot light and hope it works. But these are some of the final individual modules. And so unlike the last ones that are flat, and it's kind of difficult to see it in these images, these are very much 3D. And so there are sort of like these outside points, but you could imagine this as sort of a three-dimensional, like this is like a triangular shape here with three-dimensional intersections. And so here you can see the complexity of some of these intersections. And one of the things for me that I think was really important with this project is there's a lot of work that people do with carbon fiber with robots, but the problem with working with robots is that you can't, like, you intersect things a lot, right? The robot's just doing its thing, so it can go around in circles, and it can do certain things, but if you're a human, you can do whatever the heck you want, right? You can switch between hands, you can like pass it off to somebody else. You could basically do things you couldn't do with the robot. And so that's what I was trying to do in here. And so you begin to get some really sort of intricate details. Like this was something I had never done before either, the sort of bifurcating of one carbon fiber cable into multiple cables. And so there were like intricate intersections, but then there were also these bifurcations. And so these were the first two sort of modules I made. This one is sort of like the more traditional model. I say traditional, but it's not even really that old, maybe 10 years at max. The University of Stuttgart has a lot of sort of wound modules that are sort of in that sort of shape. But the goal for me was like, how can I make it like almost nothing? And so I started the densest, and then every module got more and more open. So you can see looking at these, like this one here, like in that one there, there's barely anything. From the first to the last module, they weigh the same amount, but because of how they're fabricated, the density changes completely. So very dense to no density. I would show it in the gallery, but it's invisible. Like literally, it's invisible in the gallery. So it was pretty funny building something that couldn't be seen by, or couldn't be photographed. But in our school, it's visible now. But so here you can see the densest piece, and then you can see the lighter ones on top. Chad with the ceramics, like we wanted to do something, like we wanted there to be a similar language. So in the original building that this was built for, it's like an old boat, what do you call it, a pier. And so it has like this open, rusted steel structure on the top, and you have the what is the bridge in Philadelphia? Man, I don't know, I'm blank. The Ben Franklin Bridge, come on. Oh, so the Ben Franklin Bridge is out the window, and so it's like this big mess of stuff. And when we first went in there, we're like, okay, let's just amp up the mess. And Chad was like, yeah, well, I'll make it even messier with the ceramics. And so we basically went for this thing where the ceramics and the carbon fiber were sort of these, just these messes of cables. And so that's what it looks like from the side. The wood's actually not doing anything. It's just sort of decorative. It holds the tray, but it's not even really necessary to hold the tray. But basically, this is what it begins to look like when you have like the 3D printed ceramics with the other pieces. Somehow everyone likes that module the best, even though it's the one I hate because I've seen it so many other times. This is one of my favorite modules right here because it's just sort of floating. The other thing about this structure that's really weird is that like there's touchdown points, but they all actually don't touch. And so all of the load from everything is actually only going to like 4 points on each side of the module. And so this is one of the, again, just another view of that. Here's the module I don't like, but everyone else seems to like it. But Chad also tried to like match the pieces that he 3D printed with the modules as well. One of the things that we're also trying to do with this is that like ceramics is typically seen as like this, like everything done by hand, right? It's very historic. Like there's a long lineage of how ceramics has been done, and carbon fiber is sort of seen as this highly technological material. And so Chad did all the ceramics like digitally, and I did everything sort of just with no planning at all, by hand. And so again, like the invisibility, it just begins to disappear, especially on the top. So the top modules were the ones I did last, and the one that was really last was that one there. And so they just basically began disappearing. But again, they're all sort of equally as strong. Like I would say that these top ones are actually probably stronger than the bottom ones because I got better at making as I went along. But anyway, that was that project. So thank you for inviting me because it made me do this project, which was it was pretty fun, I would have to admit. And Chad got out of his office, which was also a plus. So I guess I want to, like if I was to leave with some final thoughts from how I work, I guess, I don't work in a very traditional way, I would say. Like my path has been very sort of all over the place, but I guess it's just how I am. But I would say like the first thing to just remember is that like, at least for me, there are no givens, like only preconceptions to be broken. And so we think things are supposed to be done in a certain way, but why are they supposed to be done that way, right? It's because we saw it. Like you grew up in a house that looked like something, and so you think you need to make a house that looks like that. But like, why is that what it should be, right? Like another thing that I find very important, and this is even how I teach, like there are no hierarchies in collaboration. And so all of my classes are collaborative. We're all sort of at the same level. I'm like learning softwares along with my students. And so I say work with everyone, especially those with different perspectives. And that's why I work with like the most random people that you'll ever find. Because it's fun. Like they're so different than me that like we just come up with weird stuff and it's like really exciting. And I think from practicing in other countries, I think the thing that I also learned that's really important is that design is a language that transcends all borders in languages, right? And so I didn't speak Chinese, but I could go to China and talk about a project and people would understand what it was because like they could see it and they could see the drawings and they understand that, right? And in Japan, I wasn't completely fluent, but I could work in an office there because people understand what we're doing. And so just remember that, like, you should be able to put your work somewhere and not have to talk about it and have people understand it. So I think those are 3 important points for me. Just put out one other thing. So I have keep your eyes open if you want to see a weird book. This is going to be a weird book. So it's not going to be a boring book like my first book with Mahesh. Mahesh and I are doing a weird book right now. It's fictions and poetry about AI, robots, and architecture. It's going to be weird. Very, very, very graphic. It should be coming out in the fall. And so we have to have it done in like 4 weeks or 5 weeks. It's going to be a push. But that should be really fun. Lots of pink, probably. Okay, and also thank you all for having me here.